So this is the first video for Unit 13. There are a list of differentiation formulas and integration formulas that you are expected to remember for the AP exam and the semester exam. There are a few that are missing though, so we're going to go ahead and list those off before we get started with solids of revolution. Number 16 will be the inverse of tangent x dx. We can rewrite tangent x as sine x over cosine x. And then we can think about using u prime over u as a way to integrate it. Why does that keep happening? Okay. U prime over u, which means we would use natural log to integrate. Natural log of u. Now, we have to be careful when we do this because if we differentiate u, which is cosine right now, we get negative sine, which is not equivalent to the previous integration. So that means to make sure that it stays positive, we will include another negation on the outside of the integration. So now we can go ahead and integrate using natural log. So integration of u prime over u is going to be the natural log of u, which is cosine x, plus c. But since we had that negation on the outside, we will keep it for the integration. Number 17 is cotangent x, and we're integrating with respect to x. We can use the same setup that we did for tangent, except they will flip. So now we have cosine x over sine x dx. Now if we differentiate u, which is sine x, we get positive cosine, so we don't have to use any of the negations that we did for 16. So now we can just integrate using natural log. So we get the natural log of the absolute value of sine x plus c. The 18th one will be the integration of secant x with respect to x. Now integrating secant x, this will be another natural log, but we're going to be using a sum of two trig expressions. For Pythagorean identities and other differentiations and integrations, secant is always with the same trig expression. It's going to be tangent. So we have secant x plus tangent x plus c. The last one will be the integration of cosecant x dx. And you can think about the same relationship that we talked about for secant. It will be natural log again, and we are finding the sum of two trig expressions. Think back to Pythagorean identities and other formulas. It's always cosecant x and cotangent x plus c. But because we are integrating a co-function, the integration will be negative. Okay. So I would look through this, maybe make flashcards or something. If you can remember a differentiation formula, that can help lead you to integration and vice versa. Okay. One that we did not talk about a lot was number 12. If you just think of the power rule, it's when you're integrating an expression where the base is not a variable, it is a constant. So to differentiate that, you end up multiplying that same expression with the natural log of that constant, which would be natural log of a times a to the power of x. So for the differentiation, you're multiplying by natural log of a. For integration, just think of the power rule again. Instead of multiplying with that power, you divide. So you will divide that same expression by natural log of a. All right, moving on to solids of revolutions. For each solid of revolution, calculate the volume of the solid by using either disk or washer method, and then confirm the volume calculation by also using the shell method. Okay, so on the AP exam, disk and washer are required. Shell is optional. They don't tell you not to use it. They don't tell you to use it. However, it is beneficial for you to save time if you have it in your arsenal so that you can maybe figure out some of these more complex revolutions and use the shell instead of, say, like the washer. Okay. Shell isn't always the best one to use. We will take a look at some examples and compare and contrast and see which method you should be using to help maximize your time. Now, first I want to talk about disk method. The formula for disk method comes from the volume of a cylinder, okay? So if you think about the volume of a cylinder, the base of a cylinder is going to be the area of a circle, which is pi r squared. And then you give it some height, you end up with a cylinder. So we get the volume of a cylinder, which is pi r squared h, okay? Which is where we get the formula for disk method, because if we take a look at the sketch over here, this r, think of it as like a coin. We're looking at the side of a coin. It's standing up on its side. And if we were to revolve this, we would have a very tiny, thin sliced cylinder. And we have an infinite number of these cylinders as we travel along the axis of revolution. And what we want to do is add up all of these volumes of this infinite number of cylinders so that we can get the exact volume for this region that is being revolved, okay? So we have all of these cylinders, which is why disk method uses the volume of a cylinder, but we're adding up an infinite number of these volumes, which is where integration comes in, okay? Now, if we take a look, we have our pi, we have our r, which will be the radius of all of these cylinders, and then we have our dx. This dx, if we zoom in here, this is our dx, okay? And because our cylinders are sideways, that is going to be the height of each individual cylinder, okay? All right, so the radius of each cylinder is going to be different though, right? Whether if I'm over here, it's going to be significantly smaller than the radius of the cylinder that's closer to the end of the region bounded, okay? So that is why we are integrating with respect to x, all right? So that we can get every single cylinder within this integration. Now, because we are integrating with respect to x, everything needs to be in terms of x. That includes your bounds of integration, your expression, and your variable of integration, okay? All right, so if we take a look at this, the disk method was already done for you. If we look at the axis of revolution, it's horizontal, which means our r's will be vertical. Or I'm sorry, yeah, they will be vertical, but they're more specifically perpendicular to the axis of revolution, okay? So wherever your axis of revolution is and wherever your radius for each of these cylinders meet, that is going to be your bounds of integration. We need a sliding scale that tells us, okay, which cylinder am I looking at? Over here, over here, here. You're looking at all of them from x equals 0 to x equals 3, okay? And then our radius is going to be x squared, because if we think back, when we are integrating with a bar that is vertical, it is top minus bottom. Okay, so since my bar is vertical, to find an expression for r, we will do top minus bottom. Now, the top function is y equals x squared, all right? So that is the upper bound for this region. So that's the top function. The lower bound is going to be y is equal to 0, okay? So this is y equals 0. So the upper bound is y equals x squared. The lower bound is y equals 0. So that means our r is going to be x squared minus 0, which is just x squared. Now from here, it's just some algebraic manipulation, first fundamental theorem of calculus, and then from here we end up with 243 pi over 5. If you plug this in the calculator to get the exact fraction, make sure you do not include the pi because it is irrational, therefore you will never get a fraction, okay? But you can use the calculator to double check that. Now let's think about the shell method. So the shell method, it's called a shell because we're not using a full cylinder anymore. We are only using the shell of a cylinder, okay? So if we try to draw a little sketch. So I'm using the outside here, just the outside. I'm not using a full cylinder. And what it's gonna look like is it's gonna look something like this. So we come around and we're going around the edges of the cylinder. Now, this means we are dealing with the surface area of a cylinder. So if you think back to the surface area of a cylinder, we have three shapes. We have two circles, one on the top, one on the bottom, and then the area of a circle is pi r squared. Okay, now we need the area, the surface area for this wrap here, okay? If I were to, I'm gonna cut the wrap on one side, so I end up opening it up and we end up with a square, okay? So this is where I cut the wrap, right, on both sides. And then that means the length of the top is going to be the circumference of the top circle, and then the length of the bottom is the circumference of the bottom circle. Circumference of a circle is 2 pi r. And then in the middle here, where we cut the wrap, that's just going to be the height, all right? So to get the area of this shape, it's just a rectangle, so it's base times height. So we get 2 pi r h. And this is what we use for shell method. We don't care about the circles. We only care about the shell or the outside of each cylinder. So we only care about this rectangle, which is why we use 2 pi RH. So we see the 2, we see the pi, and if you use shell method, you are responsible for finding the R and the H, okay? All right, so let's clear this out and talk about a couple things. You set a timer. Don't want to go too long. Okay. So with the shell method, you need to solve for your R and you need to solve for your H, okay? Shell method is very specific because instead of your bar being perpendicular to the axis of revolution, it is now parallel, all right? So that is the key difference between disk and washer, which our bars are perpendicular, and then in shell method, the bar is parallel to the axis of revolution. So your bar is going to be your height, and then the distance between the bar and the axis of revolution will be your radius, okay? Because remember, the cylinders are sideways. Your R will always be perpendicular to the axis of revolution. When I say R, I mean radius. It's the height which we are using that is parallel to the axis of revolution. So now we are dealing with our height is going to be dy. Okay, so now we are integrating with respect to y. But the problem with this one is, we'll get to that in a second. So let's talk about this. So what is our R value going to be? Well, if I take a look, my R is going to be the radius of each cylinder. If I chose, let's do pink. If I chose this cylinder here, this particular cylinder, and I revolved it around the axis of revolution, we end up with this shell here, okay? Well, the radius is going to be in here, okay? The center of all of my cylinders are going to be at y equals 0, but the radius for this particular cylinder is y equals 2, okay? So for that cylinder, my radius is 2, but it's not always 2 for every cylinder. What if I chose a cylinder out here? If I chose this cylinder here and I revolved it, then the radius for this particular cylinder is going to be 6. And then same thing out here, I'll have a cylinder with a radius of 8. Now, if we look at this, they are all y values, okay? And if we think back to top minus bottom, the top of each of these is going to be that y value, whether it's 8, 6, 4, or 2. And the bottom of all of these, y equals 0, because they are perpendicular to the axis of revolution, and the axis of revolution is at 0. So all of my r's are going to be a y value minus 0. So we just get y. Our h value is going to be, it's parallel to the axis of revolution, therefore it's horizontal. So it's going to be right minus left. The right side here, this is just a value of 3, okay? 3 minus, and then the right side, this is our parabolic curve, y equals x squared. Now, the problem here is that you cannot mix variables, all right? R has to be in terms of y, and h has to be in terms of y because they have to match the variable of integration, which is dy. Okay, so we had y equals x squared. Just take the square root of both sides. We get square root of y is equal to x. So now I can rewrite x squared as y squared. I'm sorry, square root of y. Okay. All right, so the volume is equal to, we're going from 2, we have our 2 pi. Our bounds of integration, they have to be vertical now, okay? So the shaded region starts here at y equals 0, which we already have, so y equals 0. But now I need to find out the y value for which the shaded region stops. Okay, so if I look here, I have an intersection between x squared. Oh, it's not an intersection. This is just x equals 3 here. Yeah, because the shaded region stops at x equals 3. I see that y equals x squared crosses through x equals 3, so let's plug in 3. So if I do y is equal to 3 squared, I get 9, so that will be our upper bound. All right, our r value was y, and then our h was 3 minus the square root of y. We're integrating with respect to y. The most complicated part will be the setup, okay? So just once you get through the setup, it's going to be your algebraic manipulation, simplifying first fundamental theorem, and then maybe a little bit more simplification, okay? So from here, let's go ahead and distribute. So I have y equals 0, and then y equals 9, and then we end up with 3y minus, we have y to the power of 1 and then y to the power of 1/2. We add those powers together, we get y to the power of 3/2 dy. All right, so integrating this will just be a power rule. So we get 2 pi. Integrating 3y, it's going to become y squared. So we have 3 over 2y squared. Integrating 3/2, we end up with 5/2. So the coefficient will be 2/5. And we're integrating from 0 to 9. All right, we have our 2 pi. First fundamental theorem of calculus, we plug in the upper bound. I have 3 over 2. We will square the 9 minus 2/5. We will raise the 9 to the 5/2. And then minus the lower bound. If we plug in 0 for both of those, we just get 0 minus 0. All right, if this was a free response on the AP exam, you can stop there, okay? You don't have to simplify, but sometimes they could be a multiple choice, which will be simplified. So I'm not going to go through the simplification process. You can do that on your own. Once you do that, you should get to 243 pi over 5. Now, if you want to test it in the calculator, type everything in except for that pi, and then you should get 243 over 5, and then you can plug the pi back in. Now, when you are simplifying, just please remember your rules. You get 81, you get 9 squared, which is 81, so you have 3 times 81 over 2. And then take the square root first. If you take the square root of 9, you get 3, and then raise 3 to the power of 5. You get 3, 9, 27, 81, and then I think it's 243. So 243 times 2 over 5. And then you can simplify from there if you want to. Okay, but just be careful. Maybe practice the algebraic manipulation because you might see a multiple choice. Okay, let's see. Let's see this next problem. So now we have the bounded region. This is actually the same as the problem up top. Okay, but now we changed our, we changed our axis of revolution. So on number 1, the axis of revolution was horizontal on the x-axis. Now it's vertical on the y-axis. Okay, so shell method, we have the shell method, and it's already worked out for you. So our axis of revolution is the y-axis, which means our bar will be parallel to that. So the radius is going to be the distance between the bar and the axis of revolution, which now that it's a sliding scale for x values, because with our cylinders, the radius will be some x value. Okay, if we do right minus left, could be like 2.5 minus 0, or 1 minus 0, or 0.5 minus 0. But either way, it will just be an x value. And then our height is going to be top minus bottom. We are integrating with respect to x because the short side of the bar is changing with respect to x. So always look at the short side of the bar. For shell method, your bar is the h, okay? And then for disc and washer, the bar will be the r, the radius. So always look for the short side. We're going from 0 to 3, simple power rule integration, and then first fundamental theorem of calculus. So for this one, shell method would be the pick, all right, because you're not having to use, well, wash method you usually want to try and avoid. However, there'll be some times that you can't avoid it. They might tell you to use washer, or you won't have a way to use shell because you can't manipulate the expression provided. So it's good to know at least disc and washer, but shell is great to have as well because it is much more convenient than what we're about to do. All right, for washer method, we have our axis of revolution, which is vertical, and since we're using washer or disc, it will be perpendicular. So both of our bars will be perpendicular. So for Washoe method, remember, you're going to have a bar that is the larger cylinders, and then you'll have a smaller bar that removes the negative space, okay? So if I take a look at this, my big bar, I'm going to do right minus left. It will always start, your bars always start at the axis of revolution, all right? So if I start at the axis of revolution, I go all the way to the edge of the shaded region. That's going to be the big bar. So if I do right minus left, that x is equal to 3, and then the left is equal to 0. So this is x equals 3, x equals 0. So we end up with 3. Now, the variable x, I know we're going to be integrating with respect to y because the short side of the bars are vertical, okay? It doesn't matter because they are constants. There's no x variable involved within this, so I can just use 3 and I'm okay. However, with the little r, we are using an expression. So it's going to start from axis of revolution to where the region starts, the shaded region starts, and then we are going to do right minus left. So the right side is x squared, y equals x squared. However, we are going to be integrating with respect to y, so I'm going to use the square root of y. Remember, that's what we found in the previous problem. I needed to use y for my argument, so I just rewrite the expression so that x is isolated. And then again, the axis of revolution is at 0. Whoops. So this will be minus 0, so the radius is going to be square root of y. Sorry, the little bar. All right, this, we should be using dy. I know that this was just a setup for Washoe method, but let's go ahead and rewrite it so that it aligns with our current problem. Okay, so volume is equal to, all right, we are integrating with respect to y. We already integrated with respect to y for this problem. It was here. The bounds of integrations will stay the same no matter what method you're using, as if it's with respect to the same variable, all right? So we are going from y equals 0 to y equals 9 again. And then our big R was 3. We'll go ahead and square that, minus the little r, which is the square root of y, and then we'll square that as well. Okay. From here, we have our pi. We're integrating from 0 to 9, and we have 9 minus y dy. Integrating with respect to y, we end up with pi times 9y minus 1/2 y squared from 0 to 9. First fundamental theorem of calculus, plug in the upper bound. We get 9 times 9 minus 1/2 9 squared. Plug in the lower bound. They're both going to be 0 again, which is convenient. FRQ, you can stop here. If we keep going, we have pi. We end up with 81 minus 9 squared is just 81 over 2. So this is like 1 minus 1/2, okay? 1 minus 1/2 is just 1/2. So we get pi times 81 over 2, which is equal to 81 pi over 2, which is what we got for the first part. So really, the Washoe method wasn't too bad. It was just, I mean, the setup is always a little tedious, but shell method was definitely a little bit quicker, especially with the how we just had to integrate one term, and then first fundamental was a lot more convenient with that. Cool. All right, moving on to the next one. We're changing the bounded region, even though it looks very similar. So y equals tan x, y equals 0, x equals pi over 4, revolved about y equals 0. So tan x is going to be this upper bound. So that's y equals tan x. Y equals 0 is going to be the lower bound. And that's also the axis of revolution. And then x equals pi over 4 is going to be this right bound over here. Okay. So disk method is the first method that's being shown. And it is with respect to x because the bar is perpendicular to the axis of revolution, okay? So the short side of the bar is horizontal, so it'll be with respect to x. All right, so top minus bottom, the top bound for this bar, no matter where we are in the shaded region, will always be tangent, okay? So if we think of r is equal to top minus bottom, we have tangent x. The bottom is just y equals 0, so minus 0. And then we end up squaring that when we put it into our disk method formula. All right, so getting from this step to this step, we end up switching from tangent to secant magically somehow. Now, integrating tangent squared x, there is an integration for it, but not a lot of people are familiar with it. So whenever we see tangent squared x, or any trig expression that's squared, but you want to use another more familiar squared trig expression, like secant squared is way more familiar than tangent squared. We're using our Pythagorean identity there. So if you don't remember all of them, hopefully you at least remember this one. You can get to any of the Pythagorean identities using this. If I see tangent, that means I want sine over cosine. So I'm going to divide everything by cosine squared. And when I do that, cosine squared over cosine squared is 1. Sine squared over cosine squared is tangent squared. And then 1 over cosine squared is just secant squared. All right, and let's isolate tangent squared. So I get tangent squared x is equal to secant squared x minus 1. And now I can rewrite my integration as secant squared x minus 1 because they are equivalent. Now, secant squared x, we know that integration. We're more familiar with it. It's just tangent x, okay? And then the integration of 1 with respect to x is just x. From here, first fundamental theorem of calculus, and then you can simplify from there. So now let's see what this looks like with the shell method. All right, again, it's all about convenience. The disk method is way more convenient for this. You get it done in like 3 steps. Shell method, we might have to do a little bit more, but there are some topics in here that we need to discuss to help prepare you for the AP exam and the semester exam. So the axis of revolution is still horizontal. All right, it's going to be at y equals 0. We still have our right bound, which is pi over 4. We'll say x equals pi over 4. And then we have our upper bound, which is going to be y equals tangent x. So for shell method, our bar is going to be horizontal. It's going to be perpendicular to the axis of revolution, okay? And we need 2 variables. We need our r, which is separating. It's the distance between the axis of revolution and the bar, all right? And I'm calling them bars because no matter what method you use, that's what it's going to be. The r represents the distance from the axis of revolution to the bar. It's just that for shell method, the bar is the height instead of the radius for your cylinders. Okay, so the radius, again, if we look at this, the short side of our bar is going to be vertical, so it's with respect to y. And we want to figure out, okay, what is going to be the radius between each of these cylinders? So if I have a cylinder here, what's the radius in relation to the axis of revolution versus if I have one up here, okay? So top minus bottom, all of the radius will be some y value minus 0, okay? Every single radius for every single cylinder will be some y value minus 0. So that's our radius. So it's just y. The height, see if I can clear this out real quick. Yeah, too much going on. All right, so the height is going to be this bar here. The height will be right minus left. The right side is going to be pi over 4. The right side is going to be tangent x. However, since we are integrating with respect to y, whoops, that looks crazy. We need to rewrite y equals tangent x so that we can have y within our integration. So I'm going to take the inverse tangent of both sides, and we end up with inverse tangent of y is equal to x, so I can rewrite tangent x as inverse tangent of y. So we have our r, we have our h. Let's go ahead and set this up. So we're going 2 pi a to b. Our radius is y. And then our height is going to be pi over 4 minus inverse tangent of y, and we're integrating with respect to y. Now, our bounds of integration, we are with respect to y, so we need to get these here, okay? Because remember, your bars should be sliding along your bounds of integration, okay? So there should be a sliding scale vertically. Now we are starting at y equals 0, so our lower bound will be 0. Our upper bound, this is where y equals tangent x is meeting x equals pi over 4. So plug in pi over 4 for tangent. Tangent pi over 4 is equal to 1, so we're going to 1. Also, it's right there on the y-axis. Okay, so we have 2 pi. Let's go ahead and distribute the y. So we get pi over 4y, and then minus y arctan. I'm going to rewrite it as arctan. The negative 1 is going to confuse me. Or the inverse symbol, dy. There we go. Okay, so let's start working through it. Right small, it is going to, I can already see it's going to take a second. Okay, so we have our 2 pi. I'm going to rewrite these as 2 separate integrations. Yeah, we'll separate the 2 pi as well. So we'll have 2 pi integration from 0 to 1, pi over 4y dy minus 2 pi integration from 0 to 1, y arctangent of y. And this will be with respect to y. All right, we can pull out the pi over 4 with the 2 pi, so we get 2 pi squared over 4, which is this pi squared over 2. And we're integrating from 0 to 1. I'll go ahead and do this one. So pi squared over 2, we're integrating, we get 1/2 y squared from 0 to 1. We can go ahead and bring out the 1/2, so we get pi squared over 4. And first fundamental theorem, we end up with 1 minus 0. So we have pi squared over 4. Okay, and then let's see where we end up with the second part. Okay, so now we have, this is all minus 2 pi. Okay, we have 2, we're multiplying. So whenever we're differentiating and multiply, we use the product rule. Whenever I see this in integration, it's integration by parts, okay? Which means we have to think back to Lie8. And Lie8, the L means log, I is inverse trig, A is algebraic, T is trig, E is exponential. And whichever one we see occur in our argument first, that will be our U, okay? So if we think back, is this still charging? Okay, good. So when we're integrating and we're using U substitute or integration by parts, we think ultraviolet voodoo. So we need our U, we need our V, we need our DU, and we need our DV. So if we go through Lie8, I don't see any logs. However, I do see an inverse trig, so that will be my U, which means my dV is going to be my y, well, y dy. So differentiating U, we get 1 over, oops, that should be arctan of y, not arctan of x. Sorry about that. We get 1 over 1 plus y squared. And then if we integrate dv, we get v is equal to 1/2 y squared. You can include the c if you want to. This is a really small part of a bigger picture. All right, so this is where the ultraviolet voodoo comes in. My u is arctan of y. My v is 1/2 y squared. So I'll do 1/2 y squared arctangent of y. And then we are, let's see, subtracting the integration of v, which is 1/2 y squared, times du, which is 1 over 1 plus y squared with respect to y. Okay, so we already have this first part here, 1/2 y squared arctangent of y minus. Let's go ahead and we'll keep the 1/2 in front of the integration symbol. So we have y squared over 1 plus y squared dy. All right, so let's go through our checklist. Use substitution. We cannot use this because the degrees are the same. For u sub, the numerator needs to be 1 degree lower. We can't use inverse trig because we have that variable up top. This is going to be, it's a very specific rule, but it works, especially if you have a constant plus a variable in the denominator, but none of your integration methods are working. So I'm going to rewrite, because I see I have a 1 in the denominator. It's very, you want to try and integrate when your rational is bottom heavy. That's why we have all these methods, is that we really try to work to create a bottom heavy integration so that way we can use the methods. So I'm going to I guess it can be equal. I'm going to rewrite this as 1 plus y squared over 1 plus y squared. And if I at least get that, that can be 1. So that way I'm not dealing with a equal degree rational. However, because I added 1, I also have to subtract 1. That way we're not changing the expression, we're adding a constant and we're also subtracting it. So technically it will be equivalent to its counterpart. So if I go ahead and put this in, we have minus 2 pi, 1/2 y squared arctan y minus 1/2. We will have the integration of 1 plus y squared over 1 plus y squared. Now what I'm going to do is I'm going to separate the numerator. So I have the 1 plus y squared over 1 plus y squared, and then I'm going to subtract the last one, minus 1 over 1 plus y squared dy. So if you combine these again, they do equal this. But now what I did with my integration is that I have a part that's equal to 1, and then I have a bottom heavy part, so it's going to be easier to integrate. All right, so we'll do minus 2 pi 1/2 y squared arctan y minus, we have the 1/2. This is the, we're integrating 1. We'll go ahead and integrate. We're integrating 1 here with respect to y. So that's just going to be y. Minus, this is, well, you should recognize that. That's going to be arctan. This is going to be arctan of y when we integrate 1 over 1 plus y squared. So I have arctan of y. Now, all of this is being evaluated from 0 to 1, including the original u times v. So keep that in mind for integration by parts, is that when you separate it, sometimes we get bogged down on the back side, that we don't remember that we still have to apply the first fundamental theorem of calculus for that first part. Okay, I do notice there's a 1/2, a 1/2. I'm going to go ahead and bring that. I'm going to factor it out just so that my integration has less terms in it. When I do that, I get 2 times 1/2, which is just pi. All right, so we have y squared arctan of y minus y plus arctan of y. And we are evaluating from 0 to 1. All right, so we have our constant, pi squared over 4 minus pi. First fundamental theorem, plug in the 1, we get 1 squared. Arctan of 1 minus 1 plus arctan of 1. That's the upper bound. plug in the lower bound. That's just going, it's 0 squared, so it's going to be 0 minus 0 plus arctan of 0 is going to be 0. You cannot leave it like this, okay? You have to evaluate trig. Once you evaluate the trig after first fundamental theorem of calculus, then you can stop. All right, so we have pi squared over 4 minus pi. Arctangent of 1 is going to be here. So that's going to be pi over 4. And then we have pi over 4. Oh, that should be, oh, that is a plus. Oh, that should be plus arctan. Oh, it is in there. Minus 1 plus arctan of 1, which will be pi over 4 again. You could stop here. So if this was a free response, you could stop there. Okay. Just to see if it aligns. I solved it different than last year, so I'm going to see. Let's see, pi squared. So if we distribute the pi, we get minus pi squared over 4 plus pi. And then minus hold on. Yep, so that'll be minus, that'll be plus, and then that'll be minus pi squared over 4. Okay. These cancel out, so we get pi minus pi squared over 4, or you might see it as pi 1 minus pi over 4. Okay. So I solved it differently than last year, but this was the same answer. Okay. All right, I think that is enough for the first day. I will post the next video soon, so you have it for Thursday. All right, if you have any questions, please email me. I hope this helps, and on Thursday we'll continue with another solids revolution and cross sections.